So here we are, S2 Edexcel International, October 2016. First question, straight into hypothesis testing. 6 marks. Normally, if you know what you're doing with these things, it's quite easy marks to gain, and quite a generous mark allocation, I think I normally find. Here we've got a mobile phone company claims that each year 5% of its customers have mobile phones stolen. An insurance company claims this percentage is higher. A random sample of 30 of the mobile phone companies is taken. So the fact that we've got 30 as a fixed number of trials suggests the kind of distribution we're looking for is 30, unknown probability really, but our null hypothesis, I suppose, is that it's 0.05. That's actually our null hypothesis, H0. So looking at the actual mark scheme, 1 mark is gained for that. Another mark is actually gained for writing down the hypotheses. The null hypothesis is that it is actually 5%. And the alternative hypothesis, because the insurance claimed that it's higher, so it's one-tailed, P is actually greater than 0.05. Okay, so we're going to test our null hypothesis, do a significance test to see if this particular occurrence, 4 out of 30, is significant or not. Now it's one-tailed, so it's not difficult to find the direction of the inequality here. So we're going to find the probability that x is greater than or equal to 4, assuming the null hypothesis that p is equal to 0.05. That equals to 1 minus the probability that x is less than or equal to 3, because it's discrete. We're taking, this is all the numbers except 0, 1, 2 and 3. So this equals to, let's go to the tables to find that number. Just scrolling through to the the statistics formulae and tables. There's our normal distribution one for S1. We're going to find a binomial. We want 30 trials, so I'm going to have to scroll through to 30. Here we go. The probability is 0.05, so we're looking in the first column here. So, and it's 30. And it's less than or equal to 3. So the number we're looking for is here, 0.9392. So that's 1 minus 0.9392. And that is equal to 0.0608, which is greater than our, it's the less than, sorry, our 10%. I was going to say it's greater than, because so often it's 5%, but we've got to go with the significance level that we've got. So it's actually come below our significance level. So it's gone within, our result is significant, we think, to reject H0. So we write reject H0. That gets the final mark, gets 1 mark, so we're up to 5 marks now out of the 6, but then the next one's context. So there is evidence. I like to do what's called a belt and braces job on this. In other words, probably score the mark in 2 different ways just to be safe. There is evidence to support now the null hypothesis, or the alternative hypothesis was the insurance company's claim. Now looking at the scheme, that actually gets a mark, but I'm going to get a second time just to be safe, that the percentage of mobile phones stolen is greater than 5%. Let's say I've written a little bit more than I need to get the marks, but we certainly don't want to be missing out on all the marks. So there we go. That's the first question for part A. Right, now part B tells us it's about an approximation, but we've got a large sample now, 90, so our actual distribution is now binomial, but with 90 trials, 0.05. Let's call it y to distinguish it from the x we had in part A. Now that is approximately, because lambda, we can use the Poisson distribution because we've got a very, well, quite a small p and quite a large n. So lambda equals np. If we use that, that gives us 90 times 0.05, which is 4.5. So we're going to approximate this distribution to Poisson 4.5. Okay, and it wants us to find the critical region now for a 10% test, but it is still a one-tailed test with saying it's more than 5%. So it's still one-tailed test with H0 being greater than 5%. So we only have to look at the top hand tail. So I'm going to go back to tables, find the Poisson and look around numbers which would be close to our 10%. So there's our Poisson binomial from before. Let's get to the Poisson tables. We're looking 4.5 is what we're looking for. Now we're looking at the upper tail. So we want the first one that's below 10%. Now this would be above 10%, this number here. That's saying the probability that x is less than 6 is 0.8311. So the probability that it's more than or equal to 7 will be greater than 10%. So we can look for this number. This is the first. This one here is the first one that falls below 10%. Or above 90 if you're looking at it from the other way around. So that's what we're going to do, and we'll write that down as our and work with that to find our critical region. So to conclude what we've just seen from the tables, the probability that y is less than or equal to 7 equals to 0.9134. That means that 1 minus the probability that y is greater than or equal to 8 is equal to 0.9134, which gives us probability that y is greater than or equal to 8 is equal to 1 minus 0.9134, which is 0.0866, which is greater than our 10%. And that gives us our critical region, because if we went for the one below that, it becomes sorry, it's not greater than 10%, of course, less than 10%. And if we went for the one below that, probability that y is less than or equal to 6, we get a number here which is less than 90, which makes the thing over 10%, so it's not in our critical region. So our critical region, therefore, is that y is greater than or equal to 8, with y being obviously a whole number. Okay, so that's first question done. Now, question 2 is a continuous random variable question. It gives us the CDF, capital F, and the first thing it's doing is it's saying show that k is equal to minus 432. In this case, I would probably use the fact that f8, because the number can't be less than 8. Remember, this is basically given ft gives us the probability that t is less than t. But t can't be less than 8, so we can say that f of 8 equals to 0, and that's how we're going to work out our constant. So f of 8, because that's the smallest number in our range, it's impossible to get a number less than 0, so f of 8 is 0. So we can now just put this into our CDF. Equals 0. Obviously the 96 doesn't matter. So we're going to get 74 times 8, 592. 8 squared, 64, times 5, divide 2, is 160, plus k equals 0. So that gives us our required value for k. K is equal to minus 432 as required. There we go. Couple of marks for that. Part B, we want the probability density constant for all t. We're basically differentiating this. We don't see any reason why we can't just keep the factor of 1 over 96 outside. The CDF is going to look like 1 over 96 here. Differentiating 74 t, you get 74. And differentiating 5 over 2 squared, you get minus 5t. Differentiating the k, which is minus 432, obviously is 0. Those numbers apply between 8 and 12. And we've got 0 otherwise. Okay, so that's part B. Part C. Write down a mode. Well, we need to have some kind of picture of what this looks like. You don't need to sketch it, but you've got to have a picture in your head. I'm going to sketch it just for the purpose of demonstration here. Our PDF will look, it's going downwards because it's got a negative gradient. And it looks like this. It's unimportant, in fact, the fact that, you know, it doesn't actually go into the bottom now. I do observe that when we put in 12 there, the value of the PDF is not 0, but that's actually unimportant. The main thing is that it's going downwards from the value 8 here. So the mode is 8 because of the negative gradient. Okay, now the median, there's going to be a bit more work involved for this. It's a CDF, or we either integrate this and equate to 0.5 to work out the CDF and, well, integrate this between the limits, appropriate limits, between 8 and the median. But it's probably, since we've got a CDF, we might as well use that, I think. So we're equating this to 0.5, knowing k is minus 432. So for part D, we get 1 over 96, 74t minus 5 over 2t squared minus 432 equals 0.5. Let's multiply that out. We get 74t minus 5 over 2t squared minus 432 equals to 0.5 times 96, which is 48. Okay, let's take the 48 together and bring it over here. 5 over 2t squared minus 74t, and then it will be bringing up 40, that'll be minus 480 equals 0. I still don't really want to go to formula yet. 5t squared minus 148t plus 960. thinking about it, I've written T here. It's not wrong, but it might be nicer to write M in for median. So let's just replace all of that with M squared, M, because it's the particular value of T which represents the median, so it's kind of makes more sense to write M for it really. There we go. Wouldn't matter if you wrote it as T. Okay. So here we go. Now that's equal to 0. It does factorise that, but it might take a while to find the factors, I suppose. Or we can use a formula. So we've got M equals to 148 plus or minus the square root of 148 squared minus 4 times 5 times 960 over 10. Now you get two values there, but the only one that actually lies, I think one of the values is 20, I believe, but the other value, which doesn't lie within our range, so it can't be 20. So the one that's actually relevant is 9.6. Okay, part E says find a probability that a randomly selected lifetime has less than 9 hours. Well, there, all we have to do is put 9 into here. We don't need, again, we could integrate this, but why bother when we've already got our CDF, which will give us that value. So we got F, we're basically working out F of 9. Let's write it out. So probability that T is less than 9 equals F9, which is equal to 1 over 96, 74 times 9, minus 5 over 2 times 9 squared, minus 432. And if we work that out, we get the value, let's get in there, 21 over 64. Works out as a nice fraction, so I'll leave it as that, 21 into 64. Right, so now for the more meaty part of the question, a bit of conditional probability, which is always nice. Well, I think so anyway. So conditional probability questions always base around this kind of law, which you should always have in mind. If probability of A conditional happening is a probability that they both happen in divided by the probability of B happening. Okay, so but we're going to have to work out some stuff here, because the question says given that the lifetime is at least 9 hours, so let's work that out. Probability that it's at least 9 hours is basically saying that T is greater than, well, big T, or little t, T, not big T there, is greater than 9. Now that equals to, it can be equal to as well, but it's continuous, so it doesn't matter. That equals to 1 minus F9, and we've got F9 above, so that equals to 1 minus 21 over 64, which is equal to 43 over 64. And it says find the probability it is no more than 11 hours. Well, let's work out what the probability is without any restriction of it being more than 11. Oh, no more than 11. That's F11. So we need to put 11 back into our CDF. So that's 1 over 96 times 74 times 11 minus 5 over 2 times 11 squared minus 432. And that comes to 53 out of 64. Okay, well, that's what is less than 11 without any restriction whatsoever. But what we're going to need to find, if we're thinking of this using this formula here, that is going to be the probability. That's the probability that both of them happening. So what we're being asked for is the probability. Might look like a load of just stuff here, a bit over the top. But what we're being asked for is the probability that t is less than 11, given that t is, we know that it's greater than 9. So what we need to do is work out the probability that both of these are the case. T is less than 11 and t is greater than or equal to 9. However, thinking about it, the intersection of these two events is that it's between 9 and 11. So I'll write it like that. Just interpreting this rule here. Interpreting that. So that's t between 9 and 11. Okay, so you might start to realise why I worked this out. And that's probability that divided by the probability of the conditional thing happening, which is probability that t is greater than or equal to 9. So that equals, this is going to be F11, which we've worked out, take away F9, which we've also worked out above, divided by F9. No, 1 minus F9, but we've already worked that out, which is 43 over 64. So F11 is 53 over 64. Take away F9, which is equal to, going back to this, 21 over 64, divided by probability that t is greater than or equal to 9, which is equal to 43 out of 64, which I've worked out here. So that's why I was working this stuff out. You might have wondered at the time where I was going with this, but hopefully it makes sense. We've got all this together, coming together now. So that equals to half over 43 over 64, which is equal to 32 over 43. Okay, nice. Okay, let's do the next question. So question 3 is a binomial question with a bit of a twist, with combinations of random variables and things, the kind of stuff we did in S1. 3A, that's a bit of a gift. It just says write down the distribution of the random variable. A large number of students sat an exam. All the students answered the first question. The first question was answered correctly by 40%. The random sample of 20. It all points to a binomial. The fact that we've got a fixed number of 20 trials. We've got success or failure. 0.4 being the probability of success. So there we go. That's the first mark. Part B. They're trying to get us mixed up with the inequalities here. They're not trying to trick us, they're just trying to check if we actually know what we're doing. Students often say they're trying to trick us. It is testing to know, see if we understand what we're actually doing, which I think is fair enough. I always change to equality first. Call me dull if you like, but if it's less than 9, that means it's less than or equal to 8. So then we can say that that is the probability that x is less than or equal to 8, taking away the possibility 0, 1, 2 and 3 as well. So that's that x is less than or equal to 3. So let's go to the tables for binomial 20 to look for these numbers. Okay, scrolling back, make sure we've got the right number. It's so easy to look at the wrong thing here. We're looking for 0.4, which is the last, but this is this column here, and it's definitely 20, binomial 20, and we are looking for the numbers 8, which is 0.5956, take away the 3, which is 0.0160. So 0.5956 minus 0.0160, and that comes to a final answer of 0.5796. There we go. Part B. That's not too bad. Right, now they're mixing up a bit here for parts C and D. Let's write part C over here. Part C, students gain 7 marks if they answer the first question correctly and lose 3, so get -3 if they do not answer it correctly. And then it says find the probability the total number of points scored on the first question by 20 students is more than 0. So basically what we've got is we've got 20, if we've got 20 that, not 20, if we've got x, say, or yeah, let's call it x, that actually get it correctly, 7x, then there'll be there'll be 20 minus x who get it wrong. Okay, so x are getting it correct. Yeah, let's take the 7 out for the time. X correct and 20 minus x incorrect. But 7, they get 7 for a correct one, and they get -3 or taking away 3 if it's incorrect. And we want this to be more than 0. So solving this is not going to be difficult. 7x minus 60 plus 3x is greater than 0. So we have 10x is greater than 60. So x is greater than 6, or x is greater than or equal to 7. So that's what we're being asked for in the tables, which we're going to go to tables again in a moment. So we're being asked for the probability that x is greater than or equal to 7, which is 1 minus the probability that x is less than or equal to 6. So let's go back to the tables to find that number. So the probability of it being less than or equal to 6 is 0.2500. So that's 1 minus 0.2500, which is 0.7500. Okay, so that's part C done. Right, part D kind of related to this, but now it wants the variance of this. It says calculate the variance of the total number. Let's call that T. So it's just the T being this amount here. It's the total score. So T is equal to 7 times the correct answers, take away 3 times the incorrect ones, which we've already seen simplified. Well, let's do it again. 7x minus 60 plus 3x. So that equals to 10x minus 60. Right, okay. Now, x is just the original binomial that we've written down here. Let's work out the variance of x. There's a formula for that. I think it's in the formula book, which is for if it's binomial np1 minus p. So that's equal to 20, 0.4 times 0.6. So that equals to 4.8. So, but we don't want the variance of x. We're not being asked for that, although we're going to need it for our calculation. We want the variance of the total number. Let's call it t. Now that's equal to the variance of 10x minus 60. Right, when you're working out the variance, adding or subtracting a number makes no difference. So that's just going to be equal to 10 squared, because it's a variance, times by the variance of x. And we know the variance of x is 4.8. So it's 100 times 4.8. So that's 480. Okay, that's it. Question 3 now done. So question 4, another continuous random variable question. This time they give us the PDF fx. Right, it says so that k is equal to 1 over 8. Well, the diagram's very helpful here because we know the area underneath equals 1. So we can take this triangle here, which is equal to half times by 5 times by k, plus the area of this rectangle here, which is equal to 10.5 take 5, which is 5.5 times k, is equal to 1. So if I'll just double each of those, that's 5k plus 11k equals 2. So we have 16k equals 2, k equals to 1 over 8 as required. Okay, part B, oh it's not, it's part A2. Okay, so for part A2, well now we can just work out the gradient of this. Now we know that what this is. So M is equal to 5 divided by 5 divided by k divided by 5, which is equal to 1 over 40. Okay. Right, then it says find EX. Now we've got two bits to it here, so we have to work within the range of both of them here. So we have EX equals to the integral for this bit of x times by mx, which is 1 over 40x, between the limits 5 and 0 dx, plus the integral between 10.5 and 0 and 5 of k, which is 1 over 8 times x. We're basically using the formula EX equals to the integral from infinity to minus infinity, as written in the formula book, I believe, x of fx dx. But because the rule changes for different values, that's why we've got these two integrals with the different limits on it. Okay, so let's just set about doing that. Just a matter of taking care now, really. 1 over 40 integral from 5 to 0 of x squared dx, x squared dx, plus 10.5, 1 over 8 of x, 10.5 to 5 dx. So that equals to 1 over 40 x cubed over 3 between the limits 5 and 0, plus 1 over 8 was 1 over 16. Let's write it out like this. 1 over 2 x squared between the limits 10.5 and 5. So that equals to x cubed over 120, 5 to 0, plus x squared over 16, 10.5 to 5. So that's going to finally come to, because the zero limit doesn't have a value, so it's going to come to 5 cubed over 120 plus 10.5 squared over 16 minus 5 squared over 16. That comes to 1223 over 192. Calculator actually gives me an exact value when I do that. I'm going to SD it because it's 6.37 to 3 significant figures. So at this point I like to often give consideration to whether this answer is reasonable or not. And 6.37 does seem reasonable. We certainly expect an answer between 0 and 10.5. And 6.37, it does seem reasonable that the mean might be around there. I'd be surprised for anything less than 5. And something too close to 10.5 would also be questionable. But, you know, 6.37 seems right. We'd certainly know if we were wrong if we had the answer 11, for example. But even 10 or 9 would seem a bit questionable. 6.37 seems reasonable. Okay. Last part, find the interquartile range. Now, I suppose many of you might be thinking, well, the interquartile range, you're probably thinking of CDF perhaps, thinking of working out the CDF and using the fact that FQ1 is equal to 0.5 and FQ3 is equal to, not 0.5, 0.25 of course, and FQ3 is equal to 0.75, and working with that and working out the CDF. You can do that. You can integrate as well using the integral sign and just using integrating the fact that Q1 to 0 would be equal to 0.5 and so on. But the first thing I'm going to do is actually look at the graph and do it graphically. One thing that's clear here is we've already worked out the k is 1/8. So working out this area here, that's equal to 1/2 times 1/8 times by 5, which is 5 over 16. Why have I worked that out? Well, it didn't take me long to work it out, and it tells me something. It tells me that Q1 will be in there because 5/16 is greater than 0.25. Okay, and it also tells us, which what we might suspect anyway, is that Q3 would be in here because it's also 5 over 16 is also less than 0.75. So I've done that to just so that we can see where it is and look what rule we're we're working with. Okay, so I'm going to do this graphically. As I say, you could integrate or even work out the full PDF if you wanted to, the CDF if you wanted to, and you could integrate using the fact that integrate between 10.5 and Q3. And use the fact that that's equal to 0.25 to work up the upper quartile. And now, of course, you'd be just integrating k dx, probably a little bit. It seems like a sledgehammer to crack a nut to me. Or for Q1, you could integrate Q1 between you could integrate from Q1 to 0 we worked out m to be equal to 1 over 40. So 1 over 40x dx, and use the fact that that's equal to 0.25, and pursuing that will get you the answer. But I'm not going to do it that way because sometimes if it's linear, I just feel that integrating just, as I say, sledgehammer to crack a nut pretty well covers it. This is a linear thing and we can just do from the graph. So equivalent to what I just said about the integration, I'm going to use the fact that that area is 0.25 to work out the upper quartile, and that this area is 0.25 to work out the lower quartile. Okay, so let's work out the upper quartile first. And so I'm going to use the fact that this area here is 0.25. So we can see that 10.5, which is minus Q3, which is our length here, times by 1/8 is equal to 0.25. So multiplying that out, I get 10.5 minus Q3 equal to 2. So that gives me Q3 equals to 8.5. So that's the upper quartile worked out. I need to work out the lower quartile. Okay, so obviously I'm working with the straight line bit here. This length here, because we got the point Q1 here, and we know that M is 1/40, we know that this length here is 1/40 times Q1. So using the area of a triangle, okay, we can say that a half times by the base, which is that length there, which is Q1, okay, times by the height, which because of the gradient is 1/40, is 1/40 Q1. That's also equal to 0.25. So if I multiply that out, I'm going to get Q1 squared is equal to 80 times 0.25, which is equal to 20. So that gives us that Q1 equals the square root of 20. So the interquartile range is equal to the upper quartile take away the lower quartile, which is equal to the square 8.5 take away the square root of 20, which to three significant figures comes to 4.03. Okay, so that's question 4 done. Let's have a look at question 5. So question 5 talks about a piece of string being cut into 2 pieces at a random point. The continuous random variable L represents the length of the longer piece of string. Well, it's obviously continuous uniform because it could be cut at any random point. But it's cut into 2 pieces. The longer piece will be at least 20 centimeters, and of course it can't be more than 40 because that's just the total string. So L, the length of the longest piece of string, is uniformly distributed. The least it can be is 20, otherwise it wouldn't be the longest piece. And the most it could be is 40, otherwise we wouldn't have. It wouldn't have been cut at all. So that's our distribution. 2 marks for that. That's nice. Part B. Find the probability the length of the bit is 28 centimeters to the nearest centimeter. Well, if you drew the thing for this, the PDF, it's going between 20 and 40. But if it's 28 to the nearest centimeter, that basically means it's going to be, the length of that is going to be between 27.5 and 28.5. So effectively this is going to be 1, the width of that compared to 20. So that's equal to 1/20. So the probability that L is less than is basically between 28.5, 27.5 and 28.5 is what we're being asked for, and from the diagram, or you can calculate it, it's clear that that's 1 over 20. Okay, also pretty easy. Then it says each piece of string is used to form the perimeter of a square. Calculate the probability the area of the largest square is less than 64. So for that part, for this part, we can say for the actual perimeter of this square is obviously L. So the length of one side is L over 4. So we find the area by doing that. The area is L squared over L over 4 squared. And we require that to be less than 64. Now we know L's positive, so it's okay here, although in pure math, you know, we'd have to justify this. This was a pure maths paper, but L is positive, so we can square root that. So L over 4 has got to be less than 8. So L has got to be less than 32. So we can then say the probability that L is less than 32. Going back to our diagram, if we've got 32, if we've got 20 here, 32 here, and 40 here, and we want that, clearly that's equal to 12 over 20, which is equal to 0.6, or we can just calculate it using formula or whatever. Right, slightly more involved for part D, but shouldn't pose too much of a problem. Part D talks about the difference between the two squares, the smaller one and the larger one. Well, the largest square has area L over 4 squared. The smaller one is going to be, well, it's cut from a 40 centimetre, so it's going to be, the perimeter of the smaller one will be 40 minus 4L, 40 minus L, sorry, and that's divided by 4. Because so that will be the length of the side of the smaller square, because that's the perimeter of the smaller square. It's basically the length of the shorter piece of string. Divide that by 4 gives the length of the shorter side of the shorter square. The square in it gives you the area of that square, and we require that to be greater than 81. So I'm going to square that out. L squared over 16. Take away 1600, take away 80L plus L squared over 16 is greater than 81. So obviously L squared cancels, and when we remove that bracket there, we're going to end up with 80L minus 1600 over 16 is greater than 81. Okay, and we can work that out. That gives 80L minus 1600 is greater than 81 times 16. I'm just doing it on my calculator now. That's 1296. So that gives me 80L is greater than 2896. That gives me L is greater than 36.2. So I need now to work out the probability that it's greater than 36.2. I'll go to the diagram again. Some of you might just prefer to use a PDF or whatever, but I always look at the diagram. So 36.2 here, and we want this area, and the two extreme points are 20 and 40. So now we've got the probability that L is greater than, oh, so it's the wrong area I've got. We want it greater than 36.2, which is that area. So that will be equal to 40 minus 36.2 divided by the length from here to here, which is 20, and that comes to 0.19. Okay, so let's have a look at question 6. So question 6 is Poisson distribution. Electric company power failures occur randomly, so it says electric company at a rate of lambda every 10 weeks. Write down expression in terms of lambda for probability that fewer than 2 power failures. So let's call X Poisson lambda. Okay, and the probability that there's fewer than 2 means less than or equal to 1, which is obviously probability that X equals 0, plus the probability that X equals 1. Now the formula for Poisson, X equals to R, is equal to e to the minus lambda, and then it's lambda to the r over r factorial. So if r is 0, that's obviously reduces to e to the minus lambda. But if r is 1, then 1 factorial here, and 1 to, that becomes lambda there. So that's plus lambda e to the minus lambda. It's not necessary to write the formula, but there we go. That's the first part. Second part, if we've got, write down the expression in terms of lambda for the probability that there is exactly 1 power failure in 5 weeks. So now the rate changes to lambda over 2. And we want the probability that, let's call that y, I suppose y be Poisson lambda over 2. So we've got the probability that y is equal to 1 will be equal to, again, the formula goes like this. So with r being equal to 1, lambda, the rate is actually lambda over 2 rather than lambda, and then that will be lambda over 2 to the power of 1. So let's write it's basically lambda over 2 e to the minus lambda over 2. So relatively straightforward 4 marks to get there, just as well, because what we're about to do is going to be quite fiddly. I seem to remember doing another question on another paper recently like this, working backwards with an approximation and working out an unknown value of lambda. Really, I've been imaginative here, and they're putting us through our paces for a number of reasons, I suppose. So anyway, C1, okay, I suppose we'll get that 1 mark easy enough. It tells us we're using a normal approximation, and what we can say is that a normal approximation is justified since the rate of occurrences is large, because it's 100 lambda and we know lambda is at least 1. So not 100 lambda, 10 lambda, and we know lambda is at least 1. So the rate justifies in itself the normal approximation. Okay, so I've already used y, let's call it w, be the approximal 10 lambda which is approximation of Poisson rate 10 lambda, because it's told us that's the approximation, and it's given us a result. They've told us a probability that y is less than 15. Well, if we're using the approximation, that, let's call it W, we call it W in here, that actually means it's going to be less than or equal to 14. That's this considering the original discrete distribution. But when we go to the normal distribution, we're going to use a continuity correction. And the continuity correction, I will say, draw a number line if you need to. We've got 14 here, go back from the number line when you've changed to a non-strict inequality like that. So that means we've got the probability that Z is less than or equal to 14.5 minus the mean, which is 10 lambda, divided by the standard deviation, which is the square root of 10 lambda. And we're told that that is approximately equal to 0.0179. So we're going to have to use the tables here, but really probably better to know where we're heading before we even look at the tables, because if we think about the consequences of what we just thought through here, this number here must be negative because it's less than this and it's 0.179. So if we actually draw the standardized normal distribution with mean 0 here, okay, then we want this area here to be 0.179, or 0.0179 should I say. Well, I'm going to consider the opposite area here. Okay, if I draw this thing again, I'm going to find the Z number that corresponds to this number here from the tables. So in other words, so this is 0.0179 here. Okay, so we want to find the number that corresponds to this, and the negative of that will be the number that we're looking for, that we're going to use for the standardizing expression we've got here. So let's go to the tables now. But before we do that, what we need to do is check what this number is. It's 1 minus 0.0179. Which is 0.9821. Okay, so that's 0.9821, which is what we're looking for from the table. So now we can look for that number in our table. So we've done all the preparatory work, which is the difficult bit. It will be easy to find 0.9821 in the table, so let's do that. So the normal distribution is in S1, so we look for that. So 0.9821. Here we go. So we're looking, Z number is 2.1. So that means this number here is 2.1, but we wanted this here, which is minus 2.1. So now we can say that this is equal to minus 2.1. So here we go, 14.5 minus 10 lambda over the square root of 10 lambda equals to minus 2.1. Okay, let's multiply that out. We've got 14.5 minus 10 lambda equals to minus 2.1 times 10 lambda. So we have 10 lambda minus 2.1 times the square root of 10 lambda minus, oh, I've got 15.5, that's 14.5, minus 14.5 equals to 0. So this is actually a quadratic equation. That's a bit hidden as a quadratic, but we're basically solving, if you like. You can write a symbol for it, you know, y or w squared or whatever. You can write that this is w squared minus 2.1 w minus 14.5 equals to 0, where w equals to the square root of 10, equals to the square root of 10 lambda. So we can do that should we wish to. So basically we're using the quadratic formula. It gives us w is equal to the square root of 10 lambda is equal to minus b, which is equal to 2.1 plus or minus the square root of b squared, which is 2.1 squared. Take away 4 times by a, which is 1, times by minus 14.5, all divided by 2. Okay, when we work that out, that actually equals to 5, because the negative 1 doesn't apply. So we have 10 lambda, square root of 10 lambda equals to 5. So that gives us 10 lambda equals to 25, which finally, after quite a bit of fiddling around, gives us lambda equals to 2.5. Okay, one more question to go. So here we have another sampling distribution question, which seemed in recent years to have come on virtually every paper. There was a time when they were quite unusual, but it seems to be the rage now. Anyway, we've got a ratio 5, 2 and 1, and we've got ice scoop selling cones of either 1 scoop, 2 scoop, or for the really greedy, 3 scoops ice creams. Thankfully, not many people, fewer are actually opting for that. That's good news. Random sample of 2 customers at the ice cream shop is taken. Each customer orders a 1 scoop, a 2 scoop or a 3 scoop ice cream. So let S represent the number of ice creams ordered by these 2 customers. Possible values of S, well, first of all, if there's 2 customers, then we can, possible out values of S are 2, of course, 2, because if they both got 1 scoop. Could also be 3 if one of them had a 1 scoop and the other one had a 2 scoop. Could be 4, clearly. Either we've got one of them having a 1 and the other one having a 3, or both of them having a 2. And it could be 5 if one has a 2 scoop and the other one has a 3 scoop. Or it could be 6 if they both have a 3 scoop. So let's work out the probability of those and then put them into a table. Right, probability S equals 2. That can only happen in one way. And don't forget, if looking at the probability, individual probabilities of them, probability 1 scoop, that's equal to 5 over 8. Probability, so this is from one sample, obviously. Probability of 2 scoops is equal to 2 over 8, or 1/4. and the probability of 3 scoops is equal to 1/8. So the only way you can get 2 from a sample of 2 is if they both had 1 scoop, so that's 5/8 squared, which is 25/64. The only way they can have 3 is if one of them has a 1 scoop and the other one has a 2 scoop, but there's 2 ways of doing that because it could be 2-1 or 1-2, so that's 2 times the probability of a 1 scoop, which is 5/8, times by the probability of a 2 scoop, which is 2/8. That comes to the total of 20/64. You can cancel down if you want, but it's not necessary. Then probability that S equals 4. Now be careful here because obviously we could have 2 ways of doing it if they've got a 3 and a 1. But that we've got to double that because it could be a 1 and a 3 or a 3 and a 1. So that's 2 times the probability of a 1, which is equal to 5/8, times by the probability of a 3, which is a 1/8. Plus the probability they both actually get a 2, which is 2/8 squared. Working all those out, this here will be 10/64, this will be 4/64, so that's 14/64. Okay, so probability S equals to 5. It's either they've both got to have, one of them's got to have a 2, the other one's got to have a 3. That's 2 lots of, because it could be either direction. That's 2/8 for the 2 scoop and 1/8 for the 3 scoop. That comes to 4/64. And then we've got to allow for them both being very greedy. They've both gone for 6, they've both gone for 3, which gives a total of 6. And that's 1/8 times 1/8 squared, which is 1/64. They do want the sampling distribution, which means writing it out in a table, so don't be lazy. Particularly if the kind of person who wants to have 3 scoops in her ice cream. Right, so here we go. Right, so 2, 3, 4, 5 and 6. So we write S. I probably need to be a bit more careful with my symbols here. Little s for the particular values, capital S for the random variable, and little s that they take those particular values. And I'm just going to put unsimplified fractions in. It's just an easy way of checking that they add up to 1, because I certainly would be doing that. (14/64), 4/64, and 1/64. Okay, nearly there. Although quite a bit of work for these 3 marks. These final 3 marks is really testing our mental agility. It says a random sample of n customers at the ice cream shop is taken. Each customer orders a 1 scoop, a 2 scoop or a 3 scoop ice cream cone. The probability that more than n scoops of ice cream are ordered by these customers is greater than 0.99. Find the smallest number possible value of n. Now, I do admit, when I looked at this a few minutes ago, it took me a while to get my head around it myself. What it boils down to is that there must be at least n scoops ordered, because they all order a 1, 2 or 3. So if all of them order a 1 scoop, then there will be n scoops in total. If it only takes one of them to be more than n scoops. So for example, if n were 100 and 99 of them went for 1 scoop and 1 of them went for 2 scoops, then that's already greater than n. So what we're actually saying here is that the probability that x, if x is the number of scoops, total number of scoops, is greater than n, has got to be anything but the possibility that every single one of them has gone for a 1 scoop. And we are told that this is greater than 0.99. So, as I say, it took a bit of getting my head around that. It all boils down to the fact that the only way it can't happen is if every single person goes for 1 scoop. Otherwise, we've got more than n already. So anyway, rewriting that gives us 5a to the n has got to be less than 0.01. Okay, now we can use trial and error if you really want. I am in the habit of using logs. So if we take logs, or if we take log 5/8, n, that is going to be less than the log of 0.01. But we then have to divide through, but because this is negative, it's got to be greater than. Now it reverses the log. So that means that n is greater than 9.79, and obviously the largest integers for which this is the case, in other words the smallest n that can be, is 10. Okay, so that's a little bit of a challenge at the end there, I felt. Okay, so that's October 2016 done. I hope you are finding these videos useful. Bye.